Today we're going to work through the basics of probability. Probability is really about careful thinking and clear setup. When the situation is clearly defined, the calculations themselves tend to be straightforward. So the focus here is on learning how to read a situation, translate it into outcomes, and then decide what to do next. Probability is a way to describe how likely something is to happen. If something cannot happen at all, its probability is 0. If something is guaranteed to happen, its probability is 1. Most situations fall somewhere between those two extremes. For example, the probability that it will rain tomorrow is usually neither 0 nor 1. On the other hand, the probability of rolling a 7 on a standard 6-sided die is 0, because that outcome is impossible. The probability of rolling some number from 1 to 6 on that same die is 1, because one of those outcomes must occur. Before we calculate anything, we have to understand the language of probability, because every problem starts with vocabulary. The first term is outcome. An outcome is one single result. If you flip a coin, heads is one outcome and tails is another. If you roll a die, rolling a 4 is one outcome. If you check whether a classroom door is locked, locked is one outcome and unlocked is another. Outcomes are the building blocks. Next is the sample space. The sample space is the complete list of all possible outcomes. Think of it as writing out everything that could happen. For a coin flip, the sample space is heads and tails. For a die roll, the sample space is the numbers 1 through 6. For the classroom door example, the sample space is locked and unlocked. A quick check is to ask, is this outcome even possible? For a die roll, 7 is not in the sample space. For a coin flip, 3 heads is not in the sample space because you only flipped once. A useful check is to ask whether something could actually happen. For example, 7 is not in the sample space for a die roll because it cannot occur. An event is the outcome or group of outcomes we are interested in. An event always comes from the sample space. Rolling a 4 on a die is an event. Rolling an even number is also an event, because it includes rolling 2, 4, or 6. An event may include one outcome or several outcomes, but it must always be made up of outcomes from the sample space. Once the sample space and the event are clear, we can calculate probability when all outcomes are equally likely. The process is always the same. We count how many outcomes match the event, and we divide by how many outcomes are possible overall. Suppose a standard 6-sided die is rolled, and we want the probability of rolling a 5. The first thing to do is identify the sample space. The possible outcomes are 1, 2, 3, 4, 5, and 6. That tells us there are 6 total outcomes. Next, we identify the event. The event is rolling a 5. Looking at the sample space, only one outcome matches that event. So we have one favorable outcome out of 6 total outcomes. That gives a probability of 1/6. At this point, it's helpful to pause and check whether the result makes sense. Rolling one specific number out of 6 possibilities should feel like a relatively small chance, which matches 1/6. Now let's do a similar problem where the event includes more than one outcome. Suppose we roll a die and want the probability of rolling an even number. We start the same way. The sample space is still 1 through 6, so there are 6 total outcomes. Now we translate the word even into actual outcomes. The even numbers in the sample space are 2, 4, and 6. That gives 3 favorable outcomes. So we have 3 favorable outcomes out of 6 total outcomes. The probability is 3/6. Since 3 and 6 share a common factor of 3, we simplify 3/6 to 1/2. Again, it helps to reflect on whether this makes sense. About half the numbers on a die are even, so 1/2 is reasonable. Now let's introduce the idea of a complement. The complement of an event means the event does not happen. If the event is that it rains today, the complement is that it does not rain today. If the event is rolling a 6, the complement is rolling any number except 6. There is a key rule involving complements. The probability that an event happens and the probability that the event does not happen always add up to 1. Let's apply that rule using fractions. Suppose we roll a die and want the probability of not rolling a 6. One approach is to list what not 6 means. The outcomes 1, 2, 3, 4, and 5 all satisfy that description. That gives 5 favorable outcomes out of 6 total outcomes, so the probability is 5/6. Another approach is to use the complement rule. The probability of rolling a 6 is 1/6. Subtracting 1/6 from 1 gives 5/6. Both approaches lead to the same result. This shows why complements are useful, especially when a problem includes the word not. Now let's look at a similar idea using a different context. Imagine a jar that contains 8 red marbles and 2 blue marbles. If one marble is selected at random, there are 10 marbles total, so there are 10 possible outcomes. Suppose we want the probability of not selecting a blue marble. First, notice that not blue means selecting a red marble. There are 8 red marbles, so there are 8 favorable outcomes. That gives 8 out of 10, which simplifies to 4/5. We can also find this using the complement rule. The probability of selecting a blue marble is 2 out of 10, which simplifies to 1/5. Subtracting 1/5 from 1 gives 4/5. Again, the complement approach gives the same answer. Now we move into compound events, which involve more than one event. At this point, the wording of the problem becomes especially important. The two words to pay attention to are or and. When a problem uses the word or, we are combining possibilities. When a problem uses the word and, we are looking for both events to occur together. Let's start with an or example. Suppose a die is rolled, and we want the probability of rolling a 1 or rolling a 6. The first question to ask is whether both events can happen at the same time. On a single die roll, it is not possible to roll both a 1 and a 6. That means there is no overlap. In this case, we can add the probabilities. The probability of rolling a 1 is 1 favorable outcome out of 6 total outcomes, or 1/6. The probability of rolling a 6 is also 1 favorable outcome out of 6 total outcomes, or 1/6. Adding these gives 2/6, which simplifies to 1/3. Another way to confirm this is to list the favorable outcomes directly. The outcomes 1 and 6 are 2 outcomes out of 6 total outcomes, again giving 1/3. Now let's consider an or situation where overlap exists. Suppose we roll a die and want the probability of rolling an even number or rolling a number greater than 3. First, we translate each event. Even numbers are 2, 4, and 6. Numbers greater than 3 are 4, 5, and 6. Looking at these lists, we can see that 4 and 6 appear in both groups. That means there is overlap. To avoid double counting, we list the outcomes that satisfy at least one of the conditions. Those outcomes are 2, 4, 5, and 6. That gives 4 favorable outcomes out of 6 total outcomes. The probability is 4/6, which simplifies to 2/3. Cards give another clear example of overlap. Suppose one card is drawn from a standard deck of 52 cards, and we want the probability of drawing a heart or drawing a face card. Hearts include 13 cards. Face cards include jacks, queens, and kings, which total 12 cards. Some cards belong to both groups. The Jack of Hearts, Queen of Hearts, and King of Hearts. That overlap consists of 3 cards. Adding 13 and 12 gives 25, but subtracting the overlap of 3 gives 22 favorable cards. Out of 52 total cards, the probability is 22 out of 52, which simplifies to 11 out of 26. Now let's turn to situations that use the word and. When a problem asks for the probability that one event and another event both occur, we are interested in events happening together. Before multiplying, we ask whether the events affect each other. If one event does not change the probability of the other, the events are independent. For example, flipping a coin does not affect rolling a die. Suppose we want the probability of flipping heads and rolling a 4. The probability of flipping heads is 1/2. The probability of rolling a 4 is 1/6. Because these events are independent, we multiply the probabilities. 1/2 multiplied by 1/6 equals 1/12. Now let's look at an and situation where the events are not independent. Imagine a bag with 3 red candies and 2 blue candies. You draw one candy and do not replace it, then draw a second candy. Suppose we want the probability that both candies are red. On the first draw, the probability of red is 3 out of 5. After that draw, the bag changes. If a red candy was removed and not replaced, there are now 2 red candies left out of 4 total candies. The probability of red on the second draw is 2 out of 4, which simplifies to 1/2. To find the probability of red on the first draw and red on the second draw, we multiply 3/5 by 1/2, which gives 3/10. This example shows why we must always check whether the sample space changes. Before finishing, it helps to reinforce a consistent process. Start by identifying the sample space, then clearly define the event in words. Next, notice whether the problem uses or and. For or problems, check for overlap. For and problems, check whether one event changes the probability of the other. Following these steps keeps probability problems organized and easier to interpret. Probability becomes much clearer when each step is spelled out and connected to the situation.